Hello, everybody. Welcome back. All right. So as you can see, today we will start a new chapter. I have just uploaded this slides to the Canvas, and you can see it. You can find it in the new module called word embeddings. Let me double check if I set this correctly. Oh, yes, I think you can see it. Yeah. So this chapter is actually very closely related to the recurrent neural network chapter that we have just gone through. So the recurrent in the RN chapter, a lot of the examples that we use are natural language data, right? Are like the language modeling task, right? We are given a sentence as inputs, and the task is to predict the next word using all the previous words, right? And in the recurrent neural network example, when we convert each word into some sort of representation or some input to each time step within an RNN, then that input is a so-called one-hot vector, right? We basically need to use the vocabulary, which is all the unique words in the data, and use the index for each word in that vocabulary as the representation, the one-hot representation for each word. So there's a problem with that one-hot encoding, and the technique that we are talking about today, word embeddings, is basically an improvement towards improvements over that issue, for that one-hot encoding issue. Okay, so let's go through. Let's start from some background information here. We'll first talk about what is the technique, and we'll focus on using one model, which is called word2vec, as an example to show how word embeddings can be trained. Okay, and there's more than one, way more than actually than this word2vec model as other ways to train word embedding models. But this one, the word2vec, is one of the most famous. It is the first proposed in the year 2013, and it was basically revolutionary at that time. And it's at that time it's implemented in not in Python but in C language, and it's has its own advantage as compared to all the previous studies, as the previous models, in terms of running speed, in terms of the performance in semantic tasks, right? So we will see a lot of, I hope we can have time to cover the word2vec today. If not, we will leave it to the next lecture. Okay. All right. So let's get started with the weakness of one-hot encoding, or like what one-hot encoding is missing in modeling words. Okay. All right. So remember, when we build a one-hot vector for each word, we need to use a complete vocabulary. Say we have 10,000 unique words in it, and the first word A, right? The article word A appears as the first word, so the A will be encoded as 1000, right? And about is the second word, so it will be 010000, right? So we will use this capital capital O to indicate this is a one-hot vector. Okay. right? For example, in man, the English word man and a woman. For example, if man appears at the 5,391 position, it will be indicated by this one hot encoding vector, and a woman is indicated by this one hot vector. All right. So, for example, king, queen, apple, orange are all encoded in a similar way, right? So the problem with this type of encoding is that it doesn't, the one hot vector doesn't carry meanings. That is, if we measure the distance between any pair of the words, we'll find that they are equally distant from each other. Okay, they're equally apart from each other if the position of each word is defined by the one hot vector, right? That is determined by the nature of one hot vector, right? Because in each one hot vector, there's only one and all the other elements are zero. So no matter which two words you're choosing, you're comparing with, right? You can compare the word man with orange, or king or queen with apple, for example. If you measure distance between these two one hot vectors, the Euclidean distance that you measure is always this quantity, right? It's 1 minus 0 to the power of 2 plus 1 minus 0 to the power of 2 and with a square root, right? That is the definition of the Euclidean distance between two vectors, right? So, and the cosine distance is always 0, right? That means the two vectors, they are always perpendicular towards each other, okay? And the cosine distance is measured by the dot product, right? The dot, it's basically the dot product between two vectors normalized by the products of lengths for each vector. So since all the vectors are one hot encodings and the positions of ones are different, so if you compute the dot product between any two pairs of those one hot encodings, the cosine distance would be 0. Okay, so that said, if we want to use Euclidean distance and the cosine distance as a way to measure how semantically different or semantically related these words are towards each other, then it must be a failure, right? Because it doesn't differentiate any pair of words. Okay, so like it will directly reflected into the bad performance in language tasks. For example, if I want to predict the most likely word after I would like some orange, right? But if the model learns have encountered the first sentence above, like I would like some apple juice, right? If it recognizes the relatedness between orange and apple, then it should take advantage of that previous experience, right? Since orange is very close to apple, and it should be able to refer that next word should also be very likely to be the juice, right? But if all the words are represented with one hot vectors, then the apple and orange is not categorized, is not recognized as similar words, then it won't be helpful to predict the next word. So let's think about a way to overcome these shortcomings of one hot vectors. Okay, so actually, it has been long proposed, not just in computer science, but in first in cognitive science, that cognitive scientists have proposed such a way to represent concepts or represents objects with the so-called distributed representation. Okay, so it's like we are actually representing each object with some abstract features, right? Not with one hot vectors. So towards the left, on the right, on the left, if you look at the left part, so this is an example for one hot representation. Okay, so if you look at this first column, and the second column, third column, fourth column, these columns are features, but those features are very specific features. Like the first feature says, this is a horizontal rectangle. Then it only applies to the first object, right? So the first object only has a 1 here, but all the others are 0. So this is a similar to our one-hot encoding, right? So the second is called a vertical rectangle. Then the vector for the second object would be 0, 1, 0, 0, right? So another way is that we don't use those specific features, but we use some abstract features, right? We can extract some abstract properties of the objects, like whether it's horizontal, right? Whether it's a vertical, whether it's rectangle or ellipse, right? So for the first object, because it's rectangle and the horizontal, so the distribution, the distributed representation for it would be 1, 0, 1, 0, right? And the second one would be vertical and the rectangle, right? So as you can see, now the vectors for the first object is 1, 0, 1, 0. And the vector for the second would be 0, 1, 0, 0, 1, 1, 0. Okay. So the similarity between these two V1 and V2 is that, okay, there is a column that's shared, right? So these columns, they are shared. They're sharing one feature, which is they are both rectangle. So that means now the vector carries semantic meanings, right? So the meaning, so these V1 and V2, they are stronger than they're better than the one-hot encodings, right? Because the one-hot encoding doesn't differentiate each object from each other. It doesn't encode any relatedness or similarity, right? So this is the so-called distributed representation that use abstract features as columns, right? And we're kind of want to use the same technique to encode to represent words, right? And of course, we will need more than simply 4 features. We will need way more than that. Okay. So, for example, the distributed representation for words that we propose here is to, in this simple example, is that we will use these features. The first feature is gender, second is royal, third is age, and the fourth is food. Okay, so we can think of these represents the abstract features. And each word here in each column can have certain values associated with each feature, right? So now man and woman, they are at two extreme ends at the gender feature, right? Man is -1 and the woman is at has the 1 value, okay? And for the king, it's very close to man because king is usually a man, right? And the queen is 0.97, which is close to man. So these, we're now just focusing on the first feature, right? And for apple and orange, because they don't have such a gender property, so we will assign them as 0, which basically means it's gender neutral, okay? And for the royal feature, this feature is particularly important for the king and queen, right? So, and for the age, right, king and queen may probably have some information with age encoded. And for the food feature, there's only apple and orange that has values that are non-zero, okay? So as you can see, once we have used these 4 abstract features to describe each word, then we can basically represent each word with a vector, right? Now the man is encoded with a vector with -1, 0.01, 0.03, and 0.0. And the woman is encoded as a similar vector, but the gender feature is at two different poles, 2 different extremes values. Okay, so using these vectors, what we can do is to utilize the distance between those vectors to model the distance in semantic space. Like the meanings of those, the distance between those vectors actually carry meanings. Okay, so think about the question of the pair of words man to woman, right? If we want to use this pair of words and make an analogy to the next word king, then man is to woman as king is to which word, right? We can use these vectors to make such an inference, right? What we can do is that we take the encodings for man, which is from the first column, right? And the encodings for woman, which is from the second column, and use the distance. We like use the directly subtract the vectors of woman from the man. It will give us this distance matrix, right? And then we use that distance. We can find that the main distance is in gender, right? And if we compare the distance between king and queen, we will find a similar distance, right? King, the encoding of king minus the encoding of queen would result in a similar distance. Okay, so it's basically tell us something that's the relationship between man and woman is pretty similar to the relationship between king and queen. Okay, so such a semantic relatedness can be retrieved from these well-designed. Well, these vectors are handcrafted, right? It's not learned yet, right? But it's not resulted from a machine learning algorithm. But it's just we just arbitrarily assign those values. But it shows that as long if we are able to extract, if we are able to learn some vectors for each word in such a manner, right? Then the resulting vectors are actually meaningful in carry out in describing the relatedness between words. Okay. All right. So this is basically the effects, the effect that we want to achieve, the goal that we want to achieve. Okay. And in practice, we will actually use way more than simply 4 features. Here we will use, and in this simple example, we use 4 features, and all these 4 features have very clear meanings, right? We have gender, royal, age, and food. But in practice, word embedding technique, we will have way more features, and those features actually doesn't have very clear semantic meanings. Okay, so ideally we want to have meanings for those features, but it is not doable that we ask the first dimension to represent gender, second dimension for royal, third for age, right? So this is just imaginary words, right? We can imagine that each row of these 300 rows represents some meanings, right? But we don't actually know what they actually refer to. So the typical dimensions are 100, 200, or 300. And usually speaking, the more we use, the more accurate we can describe the meanings for words. And now the embedding vectors for each word is very long. It becomes a dense vector that has 300 dimensions. Like the encoding for apple, encoding for orange, they are in such a matter that has 300 dimensional elements in each vector. Okay. So let's look at how this particular example, like once we've got some embedding vectors, what we can achieve in a language model task. Okay. This is an demo that we use a bidirectional recurrent neural network model to carry out the named entity recognition. So as you can see, that's the first 2 words, Edward Jones, the person's name, right? They are recognized as named entities, right? And for all the other words, their output is 0 because they are not named entities. Okay. So like the next Richard Lee, the next input, Richard Lee is an apple farmer, right? So it should also be able to output that the first two sentences, the first two words are named entities recognized, right? So what about we came across some very uncommon words, say the word at the position of the orange and the apple becomes this very rare word, pitaya, right, which is a type of tropical fruit. And the cultivator, which is just another way, but not that often used way to describe the same farmer's role, right? So what about we came across these words? What we care about is that if this model can still recognize that the pitaya cultivator actually describes something that is similar to the orange farmer and the apple farmer, right? So if we are able to obtain the vectors, the embedding vectors for pitaya, and we compare it with that vector for apple, and also we have the vector that describes cultivator, which is similar to farmer, then the model that we build actually can utilize the information from apple and farmer, or from orange and farmer, to help us predict the case for the pitaya cultivator. Okay. All right, so that is the first application, which is used in language models. So because let's go back to the language model example that we talked about previously. We all used one-hot encodings, right? We didn't use the word embedding vectors, but in practice, we always use embedding vectors as inputs, right? We can load some pre-trained word embeddings for each input word, and then we will use that embedding vector at each time step as the input to the RN, not the one-hot encoding. All right. And the second application for word embeddings is actually the one that we have just covered. It's like use the word vectors to make analogies. So it's similar to the simple arithmetics between vectors. Like we want to know which word is to king as woman is to man, right? So such another word analogy task can be actually achieved by using this simple arithmetic operation. Like man and woman is in such a 300 dimensional space, but on this slide we're just visualizing into a 2D space. So if they are at such a position, then we want to find the corresponding position, the corresponding word that is in the same direction as opposed to king, right? So the queen is most likely at this position. So what we are doing is that use the distance between woman and man to find the most likely word that is in that direction. Okay, so what we can do is that we will use the distance here. So it's basically subtracting the distance between man and woman, right? And we will find the word that maximize the similarity, right? Between the words, we will find the words that maximum the similarity between this king minus such a distance, right? We are basically searching around this area. We use this first vector as a projection, and you use the king as a base and find that target area, and search the vector that maximizes the similarity, right? So if our embedding model is well trained, then the queen is most likely to be the word to be extracted, right? So that's the second application. So these analogies can actually apply to multiple types of words. So in this first work proposed by Mikolov, they actually provided a bunch of very interesting different examples, like the word embedding vectors can be used to make analogies between capital cities and the countries, right? And family members, and city in the States, for example, and like comparative words, the information between the relative information between comparative words, like bigger to bigger, bigger to big is like worse to bad. Those analogies can also be kind of extracted. And basically, I don't know what is the state of art accuracy, but at that time, the models like word2vec can actually achieve 70 to 80% accuracy in modeling the meaning of words. Okay. And the third type of task is called semantic relatedness or semantic similarity. So that is to find the most semantic related words to certain type of words, to certain input words. And the similarity, most commonly used similarity measurement is cosine similarity. Okay, so it's basically the dot product between two words normalized by the length of the two sentences. And these measurements can be useful in the applications, in the word analogy applications that's mentioned before. Similar to how list function. I don't think it's the same. So if you're referring to the parentheses, that's similar to the grammar to the syntax of Lisp programming language. I don't think we're talking about the same thing here. So the the sim function here is just a short name for to describe the cosine similarity. Okay, so it actually can be any other different similarity measurements. Okay, semantic logic in the previous slides. I don't know. It's actually not a strict. Well, here the similarities, like the analogies, like Texas to Houston is like Illinois to Chicago. So these are very strictly defined semantic logics. That's correct. Yeah. But I'm not sure. I don't know if I can answer that, how this is similar to the Lisp functions works. All right. So we can probably discuss it afterwards. Yeah, but I need to now go on with the next slide. All right. So here, this is how the cosine similarity is defined, right? So it's basically the angles between two vectors. Okay, and the cosine is bounded by the -1 and between -1 and 1 in terms of similarity. So the larger values means that the two vectors, they are very close to each other, right? And if it's -1, then the two vectors, they are pointing to the opposite directions. Okay? And Euclidean distance is also, I mean, it can be used, but in this when people want to find the similar words, it's usually the cosine similarity that's most commonly used. Okay, so for example, we can use this clustering. We can use the cosine similarity as the metrics for clustering algorithms. And so that the words that are close towards each other can be categorized into the same cluster, and then can be the higher dimensional vectors can be visualized into some lower dimensional vectors. Okay. right? You can see that's the numbers that has all in this cluster. All the numbers they are clustered into the same category. Or here these are fruits, right? And these are people, right? Oops. All right. So now let's look at because all the previous examples are based on some word embedding vectors that we assume that it's very has already been trained, that has already encoded with the accurate meanings or some sort of good representations of the word meanings. So let's look at how do we achieve that goal in training a good or successful word embedding vectors. Okay, so basically our goal here is to learn an embedding matrix. Okay, so it's a matrix because it's not just the vector for one word that we are interested in. We are actually have the goal to train the embedding vectors for all the words in our vocabulary, okay, which is basically 10,000 words, for example, in total. Okay, if we listed that 10,000 words into a vector, and each word corresponds to a 300-dimensional vector, then in total, the matrix that we want to train contains 300 times 10,000 number of parameters. Okay, so that is a total number of parameters that we need to train, which is a very large value. So this embedding matrix, we can indicate it. We can note it use the notation capital letter E. Okay, and for example, king is the has the index 3,560. Then the one-hot encoding vector for king is 0, a bunch of 0, and the 1 at the position of 3,560, right? And all the other zeros for the remaining elements, right? So the embedding of king can be obtained by using this matrix E and conduct a matrix multiplication with the one-hot vector, right? Because the one-hot vector has the length 10,000. If we use this matrix E and multiplies with the one-hot encoding for king, then that will extract, because that one, there's only one here. So the one will be multiplied with this column, and this column actually is the parameters that contains the word embeddings for the word king, right? So that is how we arrange the parameters here. So the embedding for words of index J, similar to we can use this general notation to indicate this is how we obtain the embedding for a certain word W with index J, right? And the O of W is the one-hot encoding. Okay, so in practice, when we implement this in PyTorch or TensorFlow, for example, we will not actually use the matrix multiplication, because this matrix multiplication is very inefficient. If we want to extract the word embedding vector for each word like this, but rather we will use some lookup table, which is provided in PyTorch, for example. It's called an embedding object, and it's an optimized data structure that can store those matrix-like data, and that allows for fast access to the vectors. Okay, so the learning process starts with some random initialization. Like we will initialize everything in that E with random numbers, right? At the beginning, we know nothing about We know nothing about this, how these elements, what those values should be, right? They're just randomly initialized. Then it needs to be trained through gradient descent. That means we will need to use the vectors from each, the vectors for each word, and we use that to construct some sort of training goal, right? Which consists of some loss function, for example, and that loss will be used to generate the gradients that are used to update the values for the embedding vectors. So that now leads to the question of what kind of learning goal we want to set, right? What kind of task we want to use. So the most, I mean, the earliest, at the earliest time, that people will use language task, right? Language modeling task. So like we can use the previous content word to predict the next word, right? So given the word, I would like some orange, we can predict what the next word is, okay? And because the word I comes with an embedding vector, E of I, right? And the word comes with a vector, E of wood, okay? And those vectors, they are all 300-dimensional vectors, right? 300-dimensional vectors. So if we use the previous 5 words, for example, to predict the next word, and if we're using some regular network, then on the next slide, we can see that the network basically should be like this, right? We should use the first word I to extract the the embedding vector by using the embedding matrix times the one hot vector, which gives us E of I, right? So this vector here is a 300-dimensional vector here, right? And the next word would be another 300-dimensional vector, another, and another. So assume that we use the previous 5 context words to predict the next one. Then given these 5 vectors, right? We have 5 vectors. We use these 5 vectors to predict the next word. So here we need to use some regular neural network, right? That takes this 5 times 300, which is 1,500 inputs, and to make some, for example, convert it into some hidden representations with some hidden layers, and that hidden layer will then feed into a softmax layer that computes the probabilities for each one of the 10,000 words in the vocabulary, right? Because we want to predict what the most likely word is among all the possible vocabulary. So that is the traditional method, one of the most early methods first proposed by Bengio in 2003, right? It's a neural probabilistic language model, right? That makes sense because it's a reasonable task, because the language needs to be reasonable. The next word needs to be predictable from the next word, right? And also, this method has a very significant shortcoming, which is that it's a lot of computation, right? So the softmax alone is a lot of computation, and we need to take into account the previous contents, right? And again, also I think you will soon recall that this is not the ideal case because this is not a recurrent neural network, right? The language model, as we have shown in the previous lecture, is that the recurrent structure is much more useful. I mean, much more performance in terms of predictability, in terms of the perplexity measurements as compared to non-recurrent models, right? So this type of model is, I mean, people have implemented it, and it's, I mean, a useful proof of idea to show that neural network, actually large-scale neural network, can be used to train pretty decent word embedding vectors. Yeah, but at that time, at the year 2003, that the performance of those word embedding vectors are not that satisfactory, and the training is also not that convenient to carry out. Okay, so those W1, B1, W2, B2, these are very large number of parameters. Okay, so the softmax will generate some loss, and will generate some loss, and in the back propagation stage, the gradients of that loss will be back propagated through to the input layer, which is the columns within that embedding matrix. Okay. And people have tried to improve the task by, for example, using different context lengths, right? You can use 5 left context words, or 5 right context words, or only 3 on the left, or only 3 on the right, and in a combination, 1 to the left and 1 to the right, right? So these type of different context lengths have been experimented, and we will see that actually this comparison is meaningful, because eventually we will find that sometimes use one word to predict the target word is just enough, right? As long as we have gone through the data for a sufficient amount of times. All right, so it relates to the RNN model, RNN-based language model, right? In the RNN model, we actually use one-hot vectors as inputs. And the recurrent structure is that the activations at the previous time step will be reused in the next time step, right? So actually, if you look at the parameters closely enough, the WAX, that parameter, needs to times with the xt, right? Since xt is a one-hot encoder, is a one-hot vector, then the WAX itself, it must have 10,000 columns, right? Otherwise, it won't be able to dot product with this xt, right? So this actually, it's you can think of WAX, right? WAX is 100 by 10,000, right? So it's quite similar. It's actually itself is an implicit embedding matrix, right? It's very similar to the 300 by 10,000 embedding vector, right? So that's true, because when training a language model with one-hot encoding as vectors, we are actually implicitly learning an embedding matrix, which is in such a shape, which is determined by the shape of WAX, right? So, but this training stage is even more expensive than the traditional, than the regular neural network, because of the recurrent mechanism. We need to carry out back propagation through time, which is cost us more time than the regular neural network. All right. So we will need to figure out a way to construct some type of loss, or to define some type of task, language task, that are fast to train, and also is effective in capture the meanings of the words. Okay, it should make sense. It should make sense in, for example, it should predict some context, predict some target given some context, but we don't want that context to be too long, right? If it's too many context information, then then the back propagation step will take too much time. Okay, so here's the point that we come up with the word2vec model. So first proposed in 2013, and actually the original model proposes 2 different ways to construct the learning objective, the learning goal. Okay, objective function. So it's called skipgrams and continuous bag of words, or SIBO. We'll first look at the skipgrams. Okay. All right. So given these inputs, I would like some orange juice with some chocolate chips, right? So we just, for example, we can just randomly pick up a word as a context, orange, right? And we can also randomly pick up another word, but it's within some window. For example, we set the limits of the window to be 4 words to the right, or 4 words to the forward to the left and forward to the right, if that is our window size. And for example, we randomly pick up juice as another word as our target. Okay, so next, our goal is to predict the target word from the context, right? But we will have multiple target. We can choose multiple target to predict. Okay, like for example, we can pick the word juice and the word wood and whites and sun as our target, and it actually creates that many pairs of words, pairs of context target pair, context to target pairs that will be used to construct the learning task. Okay, so how exactly the learning task constructed, right? So it's like it's also similar to the probabilistic neural network, neural language model, right? So given the context word orange, we will use the 1-hot encoding to times with the embedding matrix E. So this E still needs to be used, right? This E, it will give us the embedding vector for orange, right? But this time we don't use any additional context. We don't use the previous 5 words. We just use that word orange to predict the next target word. And it still has to be a 10,000 softmax output, which is a lot of computation, right? And in each of these softmax outputs, it will be Z1, a Z score associated, right? For each output unit in this 10,000 softmax output layer, there will be a Z here until Z 10,000, right? That's how softmax is constructed. And also the meanings for each meaning, the meaning for each output unit in the softmax is the probabilities for the target word given that context orange. For example, the first unit is the probability of the first word in the vocabulary, which is A given orange. And the probability is measured by the exponential of Z1 normalize the summation of all the exponential scores for all the units here, right? And Z2, Y hat 2 is the probability for the second word or, right? For example, and so on to all the words in the vocabulary. Okay, so this computation, the Z1s, the computation of Z1 needs to utilize a second set of parameters, right? So all these connections, they have parameters associated, right? And this second set of parameter, we will call it E prime, because this is different from this E. And the E is at the left side of this model. The E provides the inputs in this 300-dimensional vector. And this 300-dimensional vector will be multiplied with this second parameter, E prime, to construct the Z1s, which corresponds to the probabilities Y hats. Okay, and the shape of the Z hat, the Z prime is just the transpose. It's just the transpose shape of Z of E, right? It's a transpose shape which is in 10,000 by 300, but the values are totally not related to E. Okay, so E prime and the E, they are totally two different set of parameters, right? But this E prime is the shape of the shape of E prime is the transpose of the shape of E. Okay, so the E prime would be 10,000 by 300. So when we take the vector of orange, which is the 300 by 1, and multiplies with this 10,000 by 300, according to the principle of matrix computation, matrix multiplication, it will output a 10,000 by 1 vector, right? So that vector is just this Z vector, right? And this Z will now be normalized and outputs the Y hats, right? All right, so if you look at the internal of these E hats, of this E prime, and each vector, each element in Zi is just the ith row of the E prime multiplied with the orange, the vector of orange, right? So that is the meaning of the where each Z is computed. Okay, so it's just the inner product of the ith row of EI and the input 300-dimensional vector for orange. Okay, so that will determine the form of our final learning task. So for any pair of contexts, C and T, the learning task is to optimize this probability, the probability of the target word given a context word, which is actually the exponential of the Z, which is the dot product between that target word vector within the E prime matrix, the dot and its dot product between the context vector in the E without prime matrix, okay? And normalized by this summation across all the target words, okay? So still, this is a lot of computation. So I'm not saying that this is very easy to compute. It takes an instant to compute. That is not the case, because as long as you have a softmax that has a lot of outputs, these quantities takes a long time to compute. Okay, so that is how the loss looks like, because it's a softmax regression, and it's basically the cross entropy loss that we need to use, which looks like this way. All right. So, and this loss will be used to compute the gradients that are used to update the embedding matrices E. Okay. So there are some interesting discussion around which one of the two matrices are more useful. Okay, because this, while E is being trained, the E prime is also being trained, right? It's basically we call this the context matrix and the target matrix. And actually, people have found that in most cases, the context here, the context matrix E is more useful in terms of semantic tasks as opposed to the E prime. But some research has shown that if we utilize the information E prime, we can improve the performance of E a little bit. Okay. All right. So that's for the schistogram, but we are not done with all the details yet, because we have problems with softmax. The main reason is that it's really slow to compute. Remember, for each probability, we need to sum up the dot products of all the dot product of all the words in the vocabulary, right? So the solution is that in order to approximate it without having to compute all the dot product, we can use something called hierarchical softmax, for example, which basically use a binary classifier at each layer to predict whether that's target word is within the first half or the second half of the vocabulary, and then it will reach the probability for each target word, basically with the logarithm of with the cost that is proportionate to the logarithm of the vocabulary size, right? Which is a significant saving of a significant amount of time saved. Okay, and comparatively, the second part, the negative sampling task, is more often used than a hierarchical softmax. Okay, so the negative sampling is something that we will talk about more today. Okay, so it's a way to replace the softmax algorithm, the softmax output layer. It's basically redefine the task. Okay, we will simplify the learning problem a little bit. Okay, so the problem is that it's not to predict what exactly the word is, but it is actually to, given a context word, it is to predict if a random word is its target word or not, right? You see the difference here? It is not a exact prediction, but it is that we choose some random word and let it become a binary prediction. We will predict a random word whether this is a target word or not a target word, right? Of course, this is within a certain window. Okay, so that is the problem we will construct. For example, the orange and juice, right? We'll use the same example here. We'll use orange as our context, right? Then if we select juice as the random word, then of course it is within, of course it is, the label should be 1, right? It is within the window, right? But if we randomly select some other words within the whole vocabulary, if we select king, then king doesn't appear in this sentence. It doesn't appear within this context. Then the label for king, for this pair, for the pair orange and king, should be 0, right? And if we choose the doesn't appear within this sentence as either, right? So the label of it should be 0. And the word of it should also be 0, right? The book should also be 0. So as you can see, the step is to first pick some target word from the window, and that target word must have the positive label, because we deliberatively pick some word from the window, so that they are the positive examples. But also we will randomly pick some words, for example, K words from a vocabulary that are not within the window, right? So that K can be different values depending on the vocabulary size. Okay, and these are called negative examples. Okay, so now we have some positive examples and negative examples. Then we can use the data, the X pair of words and Y, to construct our training task. Okay, right? We have positive examples in the blue color, and the negative examples in the orange color. Okay, so instead of using softmax, right? We don't want to use softmax. We can use something similar to a logistic regression, right? We can use logistic regression that use the context word and the target word as inputs, and the outputs is a binary variable, right? It is the output from a sigmoid function, right? And if we visualize it, the orange vector looks like this, right? It is E times the 1-hot encoding of orange, which will give us the orange vector. And we only need to make K+1 logistic regression, because there's only K+1 pairs of words, right? And each of words, like each of these logistic regression output is just a binary prediction, right? It's just a predictor whether one word should be 1 or 0. right? So for each training example, the k negative examples are different. It's just randomly chosen, right? But also according to some strategies. Okay, and anyway, it's much faster because we're just using these k logistic regressions. It's much faster to compute than the softmax, right? And the usual values, the common values for small data sets are like 25 around 20, and the values for larger data sets around 2 to 5. Okay, so yeah, that's negative sampling, and the intuition behind is also interesting. So we can see that we use some negative examples as opposed to the positive examples, and basically it's based on assumption that we can use the co-occurrence relationship between words to determine the meanings, right? So the embedding vectors learned in this way will actually be encoded with information that the words co-occur together within a window. They will carry similar meanings, right? The words that never appeared within the same window will actually not carry the similar meanings at all, right? So it's like embeddings learned in such a way that they know which words tend to appear together in a window and which do not. Okay. So that's based on the philosophical principle that semantics can be described by words co-occurrences, right? It's like describing a word's meanings by the company it keeps, right? So it's a very interesting philosophical meanings behind this design of negative sampling strategy. Okay, and but still there's limits about the such a way of training word embedding vectors, because it's hard to distinguish like words that carry opposite meanings but still are likely to appear in the same context, right? Like the antonyms, they are not easy to distinguish from synonyms, right? So that will require some more clever engineerings. Okay. So I have some slides and I wish to cover it today. So other than the word2vec, right, there's actually more than one way to train word embedding vectors. And one of the most famous example is this so-called global vectors for word augmentations. Okay, and the short name is glove. And the learning goal behind is also very straightforward, right? Because the idea is that it wants to learn the word embeddings that minimize the cost, okay? And the cost is constructed in this way. If we look at each term of it, the capital Xij is actually the count of times that word I and J appear together in a window, right? So let's think about this intuitively, right? So if a word I and J that appears a lot within the same context, which means they tend to be similar words, right? Because they have the similar context, right? So that term is part of the context. It's applied with, comes with a negative logarithm term, right? And there's another term, which is the inner product of the two embeddings. This similar to the so this E is from those capital E is similar to the word2vec vector, right? So this E is from the embedding matrix E, okay? And based on, so such a construction of the cost function is based on the hypothesis that words that appear together more often should have more similar meanings, right? So the second, the right term here, the logarithm of xij measures how often two words appeared together. And this term here measures how semantically similar these two words are, right? So we use the subtraction here. The key is the subtraction here, right? The subtraction between these two components becomes the cost. And remember, cost is the quantity that we want to minimize, right? We will feed this cost function to the optimization algorithm, and the optimization algorithm will try to optimize this cost, which means the distance, the difference between these two parts will be squashed, right? Will be pushed to the limit as small as possible. So those words that have appeared more often together will be pushed to the points that they will have more similar meanings, right? So this is a actually a very straightforward and a smart design, and it has a very close relationship to the word2vec technique proposed. Okay, so yeah, that's glove, and we will have some parts for how word embeddings are evaluated. So I think I can leave it to the next lecture, because I don't have specific examples from PyTorch about how word embeddings are trained and how word embedding similarities can be measured. So I guess I can leave this to the next lecture. And because our next Thursday will be the recess, right? Rest and recover day for SDSU. So there will not be lecture this Thursday. So the next lecture about the final part for word embedding will be on next Tuesday. And there will be no assignments so far for the embedding as well, right? So my plan is to combine it with the next assignments. Yeah. All right. If you have any questions, you can let me know now. All right, so it's like there's no questions. Yeah, that's a good question. Let me stop recording.